Hi again, everybody, and welcome back. This example 9.5 is going to kind of cause us to have to go back into our back into the archives, if you will, of unit vectors. We talked about unit vectors in the past, where any vector has an x component and a y component. We're going to need to kind of draw upon those skills, that knowledge here, to solve this problem, because we have an object. We'll say a plate. All right, sliding across the floor right there, and all the parts of that plate all together are all in one piece, and they all collectively have a velocity of 5 meters per second. All right, in that positive x direction right there. And in fact, before we go any further, let's just label all the parts of this plate. All right, now these are three equal masses, and as you can see in the other part of the diagram right here, those masses break apart. We're going to call this mass, mass, and mass. Okay? So our mass right here of the whole thing, mass of the system, equals, I'm going to say 3m. We don't know what the mass is. You can be 1 kilogram if you want. But the initial velocity of that whole system, initial velocity of the system, equals 5.00 meters per second, as we're told, but it's in the positive x direction, right? So this is our initial velocity right here, 5 meters per second. I'm going to say x hat, right? That means in the x direction. I'm going to write it down here at the bottom too. X hat. Okay. So it's sliding across the floor. All the parts are together. They all have the same mass, and they're all moving in the same direction with the same velocity, so all the parts have the same momentum. But for some reason, the plate breaks apart. All right, it shatters into 3 exactly equal pieces, which isn't very likely, but just say it happens. Okay. We need to find out what this last piece right here, this unknown, unlabeled piece, how it's going to be moving. And let's go ahead and label these pieces mass 1, mass 2, and mass 3 right here. So mass 3 is really going to be the one that we're solving for. Okay? So one thing we need to keep in mind right here is that momentum is going to be conserved. We have to say, and we have to assume, that the net momentum of the whole system, excuse me a minute here, I need to erase something, of the system initial has to be equal to, all the way over here, no, that's not a very good place to put it, it's over here. It has to be equal to the net momentum of the system final. Okay, so these 3 masses, each with their velocities of 5 meters per second, have to add up to the various different masses here and their various different velocities after the explosion or whatever caused them to break apart. All right, the total momentum initial has to equal the total momentum final. All right. Down here at the bottom, I have this marked as 5 meters per second x hat. But I want to change something right here. All right. Let's combine, because we don't know these masses right here. We're just calling it m. But let's combine the mass and the velocity. Let's just call this 5.00 v. All right. So we can say the momentum initial of the system equals 3m times 5.00 v for velocity. All right, and that's in the x hat direction right there. Remember, velocity is a vector, and the reason I'm doing that is because, keeping these in general terms, it'll help us to compare the total beforehand momentum and the total afterwards momentum. Okay? So what does this boil down to right here? Well, the initial momentum of the system is going to be 15 mv, and m times v is momentum, right? X hat. All right, let's say that. Okay, we know v is really velocity. Sorry, v is really meters per second. But let's just call it v for now. All right. We want our total momentum on this side to add up to 15 mass units times velocity, and in the x hat direction only. So that means all the stuff going on in the y direction here has to be somehow balanced out to 0. By the way, while we're looking at the right-hand side, let's label the final velocities right here. Okay, this is so that's mass 1, right? 5.00. Let's just again call that v for velocity. 5.00 v. Instead of meters per second, just call it velocity, or v for velocity. And that's in what direction? Well, that's the y hat direction, right? Right there. That's our v final of mass 1. And v final mass 2 is 5.00 v for velocity in the x hat direction right there. So what we want to find out is, what does the final velocity, or you might say the final velocity components of mass 3, what do they have to be in order for this mass at that velocity and this mass at that velocity and this mass at some unknown velocity components to balance out to 15 mass times velocity in just the x hat direction. Okay? So I'm going to shrink this down a little bit to get a little bit more space. And we're going to do, I think that should be enough right there. Okay? So initially, again, net momentum initial of the system, that's going to be equal to, say, 15 mass times velocity units. Now we know what those units are, but we're just going to use mv for now in the x hat direction only. Okay? And they have to be equal, it has to be set equal to the net momentum final of that whole system, which is the mass times velocity of that piece plus the mass times velocity of that piece plus the mass times velocity of this piece right here. In fact, you know what? I'm going to, let's see. Well, I'm going to erase something right here. I'm going to rewrite something. Right? Just give me a second. I'm going to rewrite our net initial momentum as we're going to be a little more specific about it. All right. It is true that it is 15 meters per second, or mass times velocity units. 15 mv in the x hat. Okay, but it's also true that it is 0 mass times velocity units in the y hat direction. Does that make sense? Right? It's not moving in the y direction at all, but I want to specify that it is in fact 0 in the y direction because we've got some x and some y going on after the 3 pieces have broken up. Okay? So these are all together. Finally, after they've broken up, we have 3 different momenta, one going up this direction, one going over here, and one going who knows where down here that we're going to solve for. Okay? So let's just start by taking each of them individually. Let's look at mass 1. Okay? The final momentum of mass 1 is going to be mass 1 times 5.00 meters per second. Now, we're not going to say meters per second. We're just going to say velocity right here. 5.00 velocity y hat. Okay? That takes care of this guy right here. So it is 1 mass unit, 5 meters per second, or 5 velocity y hat. All right. How about mass 2? Mass 2 is mass 2 times 5.00 velocity. What direction is it going? That's going in the positive x hat direction, right? And lastly, we need to deal with this guy right here. Okay. Well, we know that it is, I'll write it down below. that it is mass 3. And I'm going to do a great big parenthesis right here. And it is going to be something, something, something x hat, and something, something y hat in there. The question is, what are those somethings? Well, what has to be true is that all this stuff added together right here has to balance out to 15 momentum units, mass velocity in the x direction, and none in the y direction right there. Okay? So, let's take care of the y direction first. Okay? There's nothing going on with mass 2 in the y direction, so that's fine. But look at mass 1. If this is shooting up in the y direction, we have 1 mass unit and 5 velocity units, the positive y. What can we put in here so that that will balance out to 0? Well, we've got our same mass unit right here, but we need to make this y, this velocity right here, what? Well, it's got to balance out that positive 5 velocity, so we've got to put in negative 5.00 velocity in the y direction. All right? This is almost kind of like balancing reaction equations in chemistry a little bit, but the final positive momentum here in the y direction has to be balanced out by an equal 5.00 velocity, or sorry, negative 5.0 velocity in the y hat direction. Okay? So this mass times this negative y velocity balances that out, so we've satisfied the condition that there is no final velocity, no final momentum in the y direction. Okay, so all that's left is now to make sure that we have 15 mass times velocity units in the x direction. All right, well, look at mass 2. We've got 1 mass and 5 velocity units in the x direction. All right, on this side we've got 5 MV. Over here we've got 15 MV. So that means we need to make somehow 10 MV right here. Well, we can't change the mass. But what has to be true then, in order for that to be balanced, is that the velocity must be extra. It must be greater in the x direction. What can we do to this velocity right here to have this be 5 MV and this be something to add up to 15 MV in the x direction? Well, we've got to put a 10 in here. 10 meters per second. Oh, you know what? I broke my rule. 10 velocity, we'll just say. 10 velocity, which of course we know is meters per second, in the x direction. All right, let's add everything up and see if we have if we have everything and everything balances out to what the original momentum of the system was. Okay? Well, like we said, we kind of crafted this so that the y momentum of this guy right here, 1 mass unit times 5 velocity units y hat, and this 1 mass unit times negative 5 velocity units y hat cancel out, right? So that becomes 0 right here. And let's do green for the x direction. We have 1 times 5 mass velocity units here, and 1 times 10 mass velocity units here in the x direction, and that satisfies our condition that we have 15 mass velocity units in the x direction like we have at the very outset. Okay? So, we have determined what the final velocity or velocity components of mass 3 has to be. We said that it has to be negative 5 meters per velocity, and now we can go back to saying just meters per second y hat, but it's also going to be positive 10 meters per second x hat, because that and only that satisfies the condition that the whole system had at the very beginning. That there's a 15 mass velocity momentum in the x direction and none in the y direction. We've canceled out the y's, and we've made sure the m's add up to 15 mass velocity units. And that's going to be the components of our the final velocity for mass 3. All right, so we want to find the speed and direction of the third piece. All right, well, we've done the really hard part. We just need to find the full magnitude of that third piece right there. So I'm going to draw a bigger arrow down like that, a little bit thicker, and actually with a filled-in head right there. Yeah, it's kind of ugly, isn't it? Let's try that again. Okay, it's going to look like that. That's going to be our final velocity of 3. Well, we can figure that out because we have the x and the y components now. We just need to use the Pythagorean. We can also find the direction. The direction is this angle theta right in there. Oops, I'm still drawing with the thicker pen. And we can find that too. So in order to do that, I'm just going to shrink down our work area a little bit more so that I have some more space. Okay, and then we'll just solve for the final velocity and direction of that mass 3. Okay, so we'll say the magnitude of mass 3 equals what? Well, we have our x and our y components, so we're going to use the Pythagorean, right? Square root of our x component, what's that, 10? 10 squared plus our y component, that's -5, of course -5 squared, it's just going to be 5 squared, so 5.00 squared. And that's going to give us the magnitude of the full speed of mass 3 shooting off down at that angle right there. And you know what, I was going to grab my calculator, but I'll wait till let's set up the direction, the theta right here, and then we'll solve everything all at once. Okay? So, for the theta of mass 3, what's that going to be? Well, we know if we have the x and the y components, we can find the theta by taking the inverse tangent of what? Always the y over the x, right? So 5.00, and again, I'm using just the absolute value because it doesn't really matter. This is just a reference angle, over the x component, which is 10.0 right there, and that's going to give us our angle. All right, let's grab our calculators and find the magnitude of the final velocity of mass 3, and then we're going to find that angle too. All right. And by the way, hats off to you guys for hanging in there with this one, because this one's it's not terribly difficult, but it's just a little confusing. So if you stuck with me this far, that's great. 10 squared plus 5 squared, square root of that is I got 11.2 meters per second. Okay. At what angle? All right, well, we'll do the inverse tangent of 5 over 10. That's going to be 26.6. 26.6 degrees. In what quadrant right here? Well, it's down and to the right, so that's going to be south of east, right? There's east, we're south of east there, so south of east, and that is our direction. So our final magnitude of mass 3 is going to be 11.2 meters per second at 26.6 degrees south of east. And we came to that by making sure that all the momentum of all the parts, this part, and this part right here, balanced out to the original momentum of the entire system. Okay, so thank you for following along with me this long. If you have any questions, please make sure you come see me, and I'll be glad to help you out. Thanks. I'll see you on the next one.